let's continue with some plotting, but before that, have you opened homework file yet? To introduce yourself. It shouldn't be a problematic homework. A lot of it is basically redoing in Python what you've done by hand for the first homework, just to see what the differences are. And then there's a fun heart plot, just for Valentine's Day. Whether or not you care about it, we can just plot a heart. So that's the last part of the homework, which is just doing the 2D plotting. What we introduced last time is 3D plotting, and basically your next homework is going to be much more fun in terms of plots. So let's get back. So we did some preliminary step, but we haven't plotted anything yet last time. Just a brief review. So in order to plot anything, and again, okay, I can't get to this swap displays up there to actually swap them. Let's see. Oh, wow. So for some reason, I cannot get to that swap display business. So I cannot swap and I think that's part of the reason why you don't see the mouse correctly as I move it around. Like I see it really well on my end. Swap displays, let's try this. There we go, that was it. Okay, so now we should see the mouse correctly. There we go, now we see mouse correctly. All right, we sorted that out. So what is the key in any plotting on a computer? Is that you actually have to have your hand on the exact points you want to plot. There's no, oh, computer, plot me sine Alexa or whatever, plot me sine that. Actually, probably Alexa could do it, but there's a little bit of programming behind to make it happen. But even Alexa would actually go sample a bunch of points, compute sine of x for those points, and then plot them. If Alexa is that good. And I'm sure actually you can program your Alexa's series and other assistants that you might have around you. So basically, you essentially have to have the precise points. Now in 3D, that means having, if I'm plotting something that looks a three-dimensional, that's a point in space. So it has its, with respect to some coordinate system, you have x, y, z coordinate. So that's step number one, having those points. But also when you're looking at the plot, let's say of a function, and let's say you have all of those points, how are you going to look at it? Okay? I can look at it, you're a three-dimensional object. I can look at it from this side, I can look at it from this side. What am I going to put on the plot? Okay? So you have to tell that to the computer as well. So there's an extra complexity. We're not going to go into detail of it. We're not going to do projections or anything of that sort. But you have to actually understand that any three-dimensional plotting or three-dimensional visualization, if anybody of you is playing games, okay, you always have to know where the viewer is and where they're looking. I'm standing here as a viewer, but I can be looking that way. Light can be coming from multiple sides or not at all, and so forth. And you have to have all of that information to actually see the scene. Now, our eyes do that automatically. We don't have to think about it at all. But if you want to do the same simulated on a computer, you have to be very precise in telling the computer what to do. Now, what we are really here about is just having those points. Beyond that, there are built-in functions that will do the job for us. So I do have to come up with the points. So if I'm here on this plot, what I have to come up with is for every of these grid points here, okay, I have to come up with its x and y coordinate, and then its z coordinate, how high it is up there. And then same here, right? So I have to, for all of these points, have x, y, and z. So even if I know a range of numbers that I want to plot over, like here in a simplest case, I want my x's to range from -2 to 2. So if I do a spacing of 1, that's really 1, 2, 3, 4, 5 points in x. There's much more plot here, but like let's just focus on the grid underneath that is simpler to look at. And in y space as well, -2, -1, 0, 1, and 2, so those are only 5 values of y. I still have to kind of cross them together and make all of the combinations of x and y's for those two sets. So that's my first step. And the second step is then computing z's that correspond to that. And in this case, it's -x times exponential -x squared minus y squared.
Is that in MATLAB?
Yeah, that's just typed in. This is actually how I would type it in if I was just not having power or anything. But yes, the thing, technically, in Python, you would have to do this. But MATLAB or not MATLAB, if I was using power, I would typically use that. But still, we still don't have the points. So luckily, so what we actually need is matrices. First matrix is my x coordinates of all of the points that I'm interested in. And then my second matrix is y coordinates of all of the points I'm interested in. And then I want to compute z coordinates of all of the points I'm interested in. Once I have x and y coordinates, I know that I can use simply like arrays if they're in ND type of, in NumPy type of arrays. Then I can just actually literally type in the function that I want to compute from my matrices, and I'm going to get a matrix of the same size that in corresponding spots will have precisely what I need. All right. So essentially, coming up with those points, that's what we did last time at the end of the class. So basically, I find myself x's. This is going to give me precisely -2, 0, 1, -2, -1, 0, 1, and 2. Same for y. And then there's a function that you need to remember, mesh grid in NumPy, that will give me precisely those matrices that I need. And after that, I simply compute the function based on the matrices x and y. So let's just re-execute this from last time. So this is my x. Okay. This is my y. So you can see that in x's I have -2 repeated, or basically this entire row is just repeated. And in y's I have the column of y's repeated. And that will give me all of the combinations in x and y's that I have on the grid. And then I compute z. It's kind of hard to verify whether z is computed correctly. But the way to verify really, if you wanted to see, is to take one of those points, x and y, and by hand compute what z should be, and then check in this matrix that it's actually correct. So that is at least for a couple of points. When you're doubting, you check. Great. Now we want to plot this. This, I already explained that plotting in 3D is a little bit more complex, because even if I have the points, I have to decide where to put the viewer, how to do things. But there is a module that does that. So basically, we're going to have, first module that we're going to use is the standard one for plotting. So import matplotlib pyplot as BLT. And this is really just going to give us a standard figure. So this plotting will give us a figure frame that is same for 2D or 3D. So there are certain things that we can reuse. But there are certain things that I cannot reuse. So I'm going to need another module. But I'm just going to use this 3D axis, and that is MPL Toolkit's mplot 3D. So there's an entire module. All I'm going to import from there is axis 3D. So this is handling these three-dimensional axes. These are the type of things. So when we go to have an exam, you will be able to have a cheat sheet. This is the type of thing you write down on a cheat sheet. Okay? So for any kind of 3D plotting, we need these two things. Okay, so now the first thing that I'm going to do is I'm going to create a figure. Now, we didn't create initially when I introduced PyPlot, this PLT, we did not create figure back then. We could have, but our plot that we used, plt.plot, was doing that as part of its operation. Here, however, I don't want to use any plot. I just want figure open, and then I want to modify it after. I want to add a 3D type of axis to it. So that's why I need to kind of break things down. Okay. So again, this thing has existed. We haven't introduced it because we didn't need to. Now we do. So this simply opens up empty figure. And we can actually execute just to see what happens. And it just says, hey, there's this figure. There's some default size in pixels with no axis to it. So it doesn't know what to do. It doesn't even seem to want to open a frame or anything, but it has figure as an object, some sort of initialized object. Now I want to add things to it. So I'm going to let it know that we're going to work with a 3D projection. And the way to do that is to add a subplot. Figure, add subplot. And there will be only one subplot in position 1, 1, which in this case, for this toolkit, we let it know with saying 1, 1, 1. And then I'm going to let it know, hey, we're going to do a 3D projection. So this is a 3D type of projection. So whatever is executed afterwards, it's going to figure out some sort of default place to put the viewer and see the figure. Okay. So that's why it's needed, because this projection is indeed a projection of a three-dimensional object, and it has to figure out how to do it.
Where did you put the 100 key limit?
This is just basically since it's a subplot routine, I could actually say 2, 1, 1, and then have multiple ones. But I'm just going to work with one. I'm not going to do multiple subplots. And again, this is a slightly different way to do subplots than we've introduced because it's a slightly different toolkit. Okay, so somebody else programmed it in a different way than just using it. So Python, to an extent, is like there's lots of choice. Because it's open source, you can go and post your module. Okay? So that creates variability that is not always, so this toolkit is not necessarily in sync with this one. Because whoever created it, for some reason, wanted to do things differently. It's a bit of a, sometimes too much choice, but overall it's a good thing because those choices that work out for the most people, they're the ones that survive for longer. But there is no company behind it that is working on unifying them and selling them as a product. That's why it's free. There's multiple companies using Python, but there's nobody directing it because it's not owned by a single entity. Okay? So now we will actually also do one more thing. So this will let know that the projection is 3D. But since I want, so there is a default output of this object. Those are the three-dimensional axes. I'm going to grab or store the object that is created in the process, those axes, so I can manipulate it later. And I'm going to just say AX to remind me that those are the axes You can name it anything. This fig can be any name you'd like. This can be any name you'd like. The point is that I'm grabbing the address of this object from the function so that I can manipulate it later. Otherwise, that's going to be difficult to do. And now I'm going to say, hey, plot surface is actually a function that is going to plot my points x, y, z. Those are the points that I created at the beginning. And I can grab this surface object as well. So I can modify it. For now, I'm just going to leave it be, but we're going to get back to that. So let's just do and see what we got here. Here's something. So this is actually a surface. It doesn't look as cool or smooth as the one that I had in the slides. It doesn't look colorful either. Okay. I can modify that. So what do we want to fix first? Number of points, smoothness, or the color?
It's color.
Huh?
Color.
There's one loud person saying color. Does everybody else agree we want to do color first? He needs some color on a Friday morning. All right. It's not morning anymore, right? So there's multiple color maps. The colorful or rainbow one is called Jet. So it's pre-programmed and it's available. So then I get the color. Now we want more points. Okay, more points. Here I asked for only 5, so I have a 5 by 5. That's why it's so choppy, because it's kind of linear in between those points, right? Well, then increase it to 50. 500, sure, go for it. That's prettier. 500, I don't know. That might take a moment. Let's try. Let's push it. All right. Is there a difference?
Not much.
I think it just said, I'm going to stay at 50. I don't think it actually. Let's change. What is the shape? X shape. It is 500 by 500. It doesn't look like it, really. So I think no matter how fine you make it, there's certain translation when the figure is pushed to the web browsers. So I think web browser kills some of the resolution. It doesn't look 500 by 500 to me, but okay. Let's do summer. So the point is there's multiple. So here on one of the slides, you can play with color. Okay? You can do, so I think I got jet, which is actually not on this list. You can go copper, hot, cool, winter, autumn, summer. And those are the ranges of colors that you will see. This is just selection. If you click on that link, there's way more of them. I kind of just fit however many fits into a slide. So somebody wants summer. Huh?
What's burn orange? Do that one. Burn orange.
Burn orange?
Yes, long one, burn orange.
This one? There's autumn. There's this one, AFM hot. And Vistia, whatever that is. I don't know that any of them is really burnt orange. Copper is kind of close to burnt orange, maybe. Let's try copper. There we go. Again, there's no right or wrong in color choices. It's your choice. You do sometimes have to think what shows or prints well if you're going to print it out. Okay. You don't necessarily want to be too colorful sometimes. Depends. You decide what looks good depending on the situation.
The jet one will give you cool colors and the negative numbers.
Yes, so that's useful. So that's a point well taken. You also want to kind of immediately see, you're an engineer, right? Those numbers or whatever you're plotting mean something. so in which case, cool colors are negative and positive. Let's go back to jet. Another thing that I can do, but for that I do need to name my surface somehow. I can add a color bar that is assigned to all of those positions, but I have to give it that surface object so it knows what to do the color bar for. And not Fig color bar. So figure object, you can add a color bar to a figure object that we created at the beginning, but you have to also give it the address of what you're plotting so it can actually go and figure out what colors are. And then when you execute that, I'm gonna turn off printing all of these. See? So now you actually have a color bar, and as a good engineer, you should have a color bar because those numbers hopefully mean something. All right.
Turn off,
So this is our one, huh?
Turn off print Z and print out.
Yes,
print
I did. I
Y.
just put the hashtag to turn it off. So this is a basic, and again, there are certain default views. So let's actually do a little bit of a different plot. I'm going to just move on to the next.
Can you scroll through this?
So basically, I have opening of the empty figure, then tell the figure there will be a 3D projection, and there's some math involved in projecting, so it has to know. And then there is surface plot,
Mine doesn't like.
and you can add color bar. Just a moment.
Never mind. Never mind.
You could do all kinds of similar things and plot it as a wireframe. Let's give that a shot. So let me just give you some options visually before we execute them. So this is, I used a slightly different function in the file that I posted for you. This one was 2 minus x squared minus y squared. Again, it's just a different function. Today or last time and today I decided to use the function that I had in this initial slide. It doesn't really matter. This is what's called a surface plot. This is a wireframe plot. So you can do that. This is a contour, but this is actually a three-dimensional contour type. Okay. And then you could also project contours, in which case there is actually a pyplot command, plt.contour. So those are projected contours. So let's give those a shot just to see how they're done. So I'm actually going to just open a new figure. How do I let it know that it's going to be a 3D figure? Something projection 3D, but what do I do with that?
Big equals big dot add underscore subplot.
This is just default one figure, position 1, 1. And then projection equals to 3D. So a lot of programming you will see in Python works this way. When you have a function, if I didn't set the projection, it would be set to a default, which is 2D. Right? But I can modify it, and the way I modify it, this is sort of a reserved word that I can set to 3D. Now, if I try 4D, it's probably not going to work, right? So it has to be set to options that exist. This is how you pass options. That was the same way as in plot, you have that line width. You can set it to 2, or you can add label to a plot, and so forth. So those are some options. If you don't set them, they're there, set to some default value. So it still works, but you have an option to modify it. So this is telling it that it's going to be a 3D projection. Okay, and then I can just say, instead of plotting surface, I can just do plot wireframe. But still that data is X, Y, and Z. That is the key point, and I need to type correctly. So now it's quite a dense wireframe. You can also, let's learn how to change the view. So the way views work, I can say axis, initialize view, view init to 0, 30. What that means is there's so-called elevation in angles or degrees that is here 0. So elevation azimuth. Elevation is my elevation should be as if so here if I say 0, I'm on a 0 elevation. I'm sitting on the XY plane. And then shift the XY plane by 30 degrees. Okay. So you can do that. And then you will kind of do a side view, which I guess that default view works a little better actually at this time. What happens if my elevation is 90 degrees? I will kind of do this, right? Well, that's not very insightful for this plot. So the point is with 3D projections, you kind of sometimes have to play it in like what is the best angle to actually see something. Yes?
You can change the color.
And I squashed my Z-axis to nothing. Huh?
You can change the color on wireframe, correct?
I would think so. I haven't tried. You can check out online how to do that. I'm pretty certain. I don't think you can do a color map. So I don't think color map because it just doesn't do color map. But let's give it a try. I don't think so. No. Wireframe is like, sorry. I don't do color map. But if somebody can go online and check plot wireframe function, there's probably a way to change the color. And please report back. So those are views. There is other things that I can actually set. So this is the 3D plot. So setting labels to the axis. Let me actually just change this view to 0, 30 was much prettier. No, actually default was just fine. I'm gonna stick with the default. So there's a way to set the X label, Y label, Z label. It's just a slightly different function because we're working with a different toolkit. So we're gonna do that. And the function is xset X label. Since I have nothing more smarter than say, oops. I cannot say anything more about these axes other than their X, Y, and Z, but that might be still important information. And you can equally set Z axis, but for Z axis, I'm probably not confused which one is Z. For X and Y, I might be confused which one is which one. And it's also telling you that the way it's actually setting up this text is that it's putting it in the position 0.50 as Y. Just if you were wondering. I could also set limits, and that I do with X limit. Let's do X limit to what our range was -2,2. So let's just snap it to -2,2. And X set Y limit -2,2. So it's a slightly different way to set limits than for 2D plots. And then my z would probably go to 0.3, it looks like. Minus 0.3, minus 0.3, so let's do that. Not minus 0.3. So then it's as large as as it could be for seeing the entire file. So what we learned in this Go is how to label my axes and how to set their limits. And I turned off initializing the view because 030 didn't really give me what I wanted to. And 9030 was even worse. So it all depends. And then we could do the same thing. I'm actually gonna do it in place. We could do a contour plot. And instead of retyping everything, I can just do contour. It's a 3-dimensional contour. Looks funny. Contour. XYZ. So contours are lines on in my 3-dimensional world where my elevation doesn't change. So it picks a selection of those and plots them. Contours is if whenever you go hiking, you will get the contour map of your park. Right? It's just a projected one. Hello?
Is this the chemical engineering?
It is a chemical engineering building, but we're petroleum engineers. Is that a problem?
Big order for 11:45 for this room.
1:45?
11:45.
That's in 10 minutes. Yes. We'll take lunch.
We'll take
We'll take lunch. And so it's somebody who's coming afterward.
This is 200 West Dean Keaton, isn't it? I'm
Yes.
at 200 East Dean Keaton. This is I guess.
East Dean Keaton might be.
Probably right.
Yeah.
Well, it says chemical engineering building.
Yes.
So then it is West. This is chemical engineering. Which room? Which room?
It says
Which room? Are you in CPE 2.216?
This
I think
is the building.
CPE 2.216.
chemical engineering.
Uh-huh.
Yes.
Room 2.210.
This is the room, but we have a class until 11:50. And then something is probably
Maybe
here at
it's-
noon.
Okay.
Yeah, it happens with 2.216. There's an event at lunch with the Society of Petrologists and Well Log Analysts.
But is that the
They will
same
have food.
as PWLA?
Yes, they
Maybe.
have an event.
We should have just taken that lunch.
Three
I don't know.
burritos.
No, those are not burritos. Those are sandwiches.
Oh,
There might be something else. So
maybe something else.
either way, I'm cool with sandwiches. Whenever somebody offers me lunch, I'm not terribly picky. You want to feed me? Feed me. Anyway, I'm an omnivore whenever it comes to, especially, I don't think you all are still, are yet into the mode that you're cooking for yourself. Once you start cooking for yourself, anybody wants to offer me food. Leftovers are good. Everything works. Just give me food. I don't want to cook. Anyway. I'm not picky at all. Yeah, anyway. All right, very, contours. So contours are lines of the same elevation, and you can plot a selection of them. Here they're actually shown in 3D. I'm not gonna go, you can actually go and in the points that are, in the slides that I posted, and we're gonna have a homework for plotting them in 2D. So this is an example for this function, how contour looks like projected in a plane. Yes, and that's this. It's available in PLT. Yes?
Is that really actually map?
Yeah. Maps are this. Precisely. So the point for hiking, the learning point for hiking from here is that if you want strenuous exercise, you cross contours orthogonally, because then you're changing elevation. If you want an easy walk, pick a contour and keep walking on a contour. It's going to be flat, right? And then there's also a difference. You're going to see a gradient in elevation. So if these things bunch up, they're typically evenly spaced. So here's every 10. Okay? So if I change whatever 10 here is, elevation of 10 over a short distance, that means that I'm steep. Okay? So if you want a real strenuous exercise, you pick part of the park that has contour lines bunched up. Okay? If they're spread out, then that's an easy, yes? Because again, contours are plotted at typically at certain spacing. And if that spacing is, if the contours that are next to each other are very close together, that means that I switched to a different height over a short distance. Okay? And otherwise, now that all of that is true for reservoirs as well. None of the reservoirs in petroleum engineering are nice and flat boxes. Okay? They change. Your formation, initially in sedimentary rocks, everything is kind of laid out straight. But then over geologic time, certain portions will come up, certain portions will go down, certain portions will get broken apart, so you'll have faulting, right? All of those will change. Actually, you will look at those using contour plots. It's just typically contour plots in subsurface are looking at depth, not height. So it's negative. Even if it's not shown as negative, it's typically meaning depth. So your Z direction points downwards in subsurface. All right. All right, so have fun with color maps as much as you'd like.
Do we need to?
And if you want to save any of these figures, yes,
Go ahead.
there is a Savefig feature. Okay, so you can just type in something like that into the plot. So if I just want to save it, I'm going to say save fig. So this type of function, save figure, or ability to save figure travels with my figure object. So I can do that in any figure that is created with PLT function. This is contour. And then extension. So it's going to be smart enough to figure out standard extensions for figures. JPEG, TIFF, PNG. One of those will work. So if I do that, nothing will happen here. However, if I actually go to my, so I should see contours seconds ago. So this is the figure that I saved. Okay? And that figure is now in your folder. You can import it into a document. You can work with it. Post it on your website.
And you said that we can't do this with PLT, right?
Anytime you create that figure with a PLT function, so all of those plot functions, they will automatically have that. You will just have to save figure as an object after you open the function in order to manipulate that. Right?
Do we need to import matplotlib, matplot, contour?
Yes, so here I didn't import in this part because that I already did earlier.
Oh, I'm talking about on the PowerPoint slides.
So these are two things that you need to import.
Yes.
Yeah.
I'm talking about on the PowerPoint slide.
For this?
Go up to the different graphs. There you go, right there.
Yeah.
Matplotlib.5.
So this is all part of the Axis 3D. I just kind of gave it the last name.
I'm talking about the one on the lower right.
This one?
Yeah.
This is your PLT.
Okay.
Import matplotlib.pyplot as PLT. That's
Okay.
what we do all the time. So this is contour is already available.
Okay, gotcha.
Okay. So you can also, if you were finding these fun, you can go and play with some demos online. Get at it. Okay, there are different ones. You can try them all if you'd like. All right, and these are just some examples from my research that are surface plots. I often work on computing fracture conductivity or permeability. So in a lot of tight reservoirs, fracture is the only thing that is technically open. Everything else, even if it's open, it's flowing so slowly that it's not going to catch up to the fracture. And here's one that has some partial cementation, pretty partial cementation. These are quartz crystals. So a lot of sandstones have a lot of quartz. That quartz then gets dissolved in water, and it also gets cemented as you go. And these different crystals can start growing and bridging across these fractures. And if they manage to bridge across, they're going to keep it open. So these are really some really cool fractures. They're not your parallel plates as we typically envision fractures. And they're actually, whoa. Sorry. My phones go to my email. Bye. And apparently my multiple emails. All right. Really? Bye. All right. This is useful and not so useful feature. Where was I? Of my phones being directed to my email when my email is open. All right. So basically you can actually see what's left of this pore space in between all of these crystals. Not much really. But the surface of these crystals is going to give me, so this is basic surface colored in this kind of UT orangey color. Okay. And then this is actually plot height of all of these, well, how much pore space, what is the height of the pore space I have. And a lot of it is 0 because it's not flowing at all. And then some of these large portions are pretty open. So this is called aperture of the fracture. So this is some 3D plots that you can see. I also do a lot of simulation. So basically, this is a variant of a contour command that tells me, so this is a mock porous medium that has a bit of an opening, also kind of a two-dimensional fracture in between grains. And I can see invading gas trying to come in. But I use the variant of contour that also fills the region with a full color. So these grains are filled with black, and this gas is filled in as with red. So I can see how invasion proceeds, and I can plot that. Okay? This is actually seeing all of the individual contours. So as it proceeds, these are all of the contours in time as they change. Okay? So I'm just plotting them with alternative red and green. Now in terms of plotting things, what I didn't consider is that some people don't see red and green. So this is actually a poor choice of coloring, okay? Because that would be all gray for the person that doesn't see red and green. So this is certain color choices that you should actually pay attention to. But I grabbed this because it's actually published in a paper. So my bad choice is published in a paper, okay? So that's something to think about. All right, now let's move on. We literally have a couple of minutes, but we can have some fun with input and output. We're going to switch from plotting to, okay, great. Now I want to get some data from a file and also be able to dump data into a file. Okay? So we've learned how to create our arrays or information without files. Now we're going to do it with the file. So I'm going to actually open a new one here. File, open new, Python 3. And I'm going to call this one, once it lets me call it something, okay, Lecture 2.6 Spring 2019. As usual, I have uploaded 2.6, and that one has much more comments than I have the time to type in during the class. So if you have that, or if you don't type quickly enough, things are posted for you on Canvas. So now we're actually going to learn some basic inputs. So very simple type of input is grabbing something that I type in, and I will use function input for that. And typically, you want to prompt the user to do something. You don't just do input. And that prompt that you wanted to print out, you put as, you pass to this function input. So I'm going to say, hey, what is your name? I'm going to ask the user. And I want to remember what user puts in. So I'm going to give that variable a name. And I'm going to be very inventive. I'm going to say name equals to input. And then when I execute, Python is asking me, what is your name? Masha. And now something supposedly happened. Well, I can see what name is by printing it. Haha. So basically that means that, now in that name I have grabbed, and this is what all of these web forms or whatever are doing, right, when you're typing something in. They're giving it a variable and storing that result so then they can use that result later. Well, we kind of print it here, but we can actually be talkative here. Oh, great. Nice to meet you, Masha. So this gives an appearance of artificial intelligence behind, except that it's not. Okay. So what we see here is that there's print command. So far we just used print a variable and it would just dump the variable. Okay. Here what I'm telling you is actually you can add text to it so you can tell the users in some way what it is that you're printing. Okay. So when we were printing x, we could have said print x equals to and then x. So what comma does here is just takes the first part, gives it the space, and then prints whatever variable you have afterwards. Yes?
So say you do a number in there. Is that number stored as a number or a string?
Great question. Does everybody allow me one more minute here? Since the question prompted it. So I'm going to say, how old are you? And comma, name, comma. Oops, oh, yeah. I cannot be too talkative, this is input function. How old are you? And I'm 41, thanks for asking. So now what is this age? I can print age. It prints correctly. I can ask for a type of age. It is string. So if I want to compute with age, okay, if I say print age plus 2, that should be 43, but it has issues with that, okay? But we said that we can do basic conversions, so I can convert it to integer, and then I can work with it. So whatever is stored is a string, but you can convert it if you know it's a number. Yeah? So any kind of conversions can be made as long as they make sense. All right. You brought food for us. Great. Thank you.
Sorry, we just have to